This is AP Calculus BC, and in this video I'm going to talk about sections 8.1 and 8.2. Section 8.1 is titled Modeling with Differential Equations, and really what it is just an introduction into the basics of differential equations. Now, as we go through this unit, first thing, this unit's going to be very short. There's not a ton of material that we're going to cover here. We don't go very in depth on differential equations. We really primarily talk about one type of differential equation, which is referred to as a separable differential equation. And we'll talk about in section 8.2 about how we can solve these. But really in section 8.1, we're just kind of getting the idea of what a differential equation is, and we're talking a little bit about what the solutions are going to look like. So when we talk about a differential equation, we're just talking about an equation with differentials in it. We've seen these a little bit before. We saw them when we were taking derivatives and we would get dy dx. We were actually creating a differential equation. But we saw it a lot when we were doing integrals, when we were doing antiderivatives, and we would start with dy dx and we'd want to work back to the original function. We kind of were solving differential equations without going through the steps that I'm going to show you here. Okay, so one of the most basic types of differential equations that we're going to see is one that has to do with exponential growth and exponential decay. And you can see that we've got this equation here for population. It says dp dt is k times p. So that means the rate of change of my population growth is equal to some proportionality constant times the population at that particular point in time. Okay, so that is how I find the rate of change of the population. And what we're going to want to do is we're going to want to say, okay, from that, what's the actual function that models the population at any point in time? Okay, so that's really where we're going to go with this, is solving these differential equations. Now, when we solve these, I'm not going to go through the steps here. I'll go through them later. What we'll do is we'll do a method called separation of variables, and we'll come up with what we call a general solution, which means this is the solution for all of the functions that have the differential equation or the derivative k times p. Okay, notice we have c e to the kt power. C is an arbitrary constant. So this is what we call a general solution because it represents an infinite number of curves. Depending on what that c value is, we can have different graphs. And so this graph over on the right here is showing you that when I have p of t is equal to c e to the kt, I really have an infinite number of curves that can be modeled by that. If the c value is positive or negative, it's going to shift this graph one way or the other. So we can have also the graph is going to change by that scalar value of c. So if c is 1 or 2 or 5 or 1,000, it's going to change slightly what my graph looks like. But overall, if you look at those graphs that are drawn here, this is just a sample of some of the solution curves. They all have the same general behavior. Okay, so that's really what we're getting at when we say a general solution. Okay, so for example, we can find what we call a particular solution, which is just one of those curves in that graph, if we know a point that our function has to go through. So for example here, they're telling you that the initial population is 2.5, then we can find the particular solution. Population at any point in time is 2.5 e to the kt power, and then from there, if we needed to use this for any sort of application, we would have to have another point, and then we could find that proportionality constant. Okay, so 8.1, you're not going to do a whole lot in this section other than just get a feel for what these differential equations are that we're going to be working with. Okay, let's move on to section 8.2. In section 8.2, we're going to start talking about how to actually solve these differential equations. And like I mentioned in the last section, we're going to use a method called separation of variables. So there are a lot of different types of differential equations. And I've mentioned this before, but differential equations it's actually a topic that you could specialize in, and you could study differential equations in college and graduate school and beyond, and you could study differential equations for years and years and years because there's so many different types. There are certain types of differential equations that can be solved. There are certain types of differential equations that you can never solve and get an exact solution for. And then we get into a bunch of approximation methods that we can use to solve these as well. So we're going to look at primarily one type, which is called a separable differential equation. Okay, so here is a differential equation that what we're trying to solve. And when it says solve, what it means is we're trying to figure out what is y in terms of x. Okay, so the way we do this is we separate the variables. We try to get all the y's on one side and all the x's on the other. So I've got this one already worked out. You can see what I've done here is I've multiplied the y squared over to the dy. I've multiplied the dx over to the x squared. And now I've got the variables separated, and I'm going to integrate both sides. So we take the antiderivative on both sides. Notice I only have a plus c on the right side because really there'd be an arbitrary constant on the left side and the right side. We just kind of skip that step and combine them all together into an arbitrary constant on the right side. And then from there we can solve for y. Multiply by 3. Notice here we have a 3c. A lot of times I won't do that. I'll show you that when I solve differential equation here in a second. But we can leave it as 3c, or we can write it as sort of a new arbitrary constant. But then that gives me what we call the general solution, because like we just saw in section 8.1, there's an infinite number of curves that look like that, depending on what the c value is. So if we know a point that our function has to go through, or our solution curve has to go through, that allows us to solve for the c. And you can see I did that here. I plugged into my equation. I plugged in x is 0 and y is 2. That gave me a c value of 8. And now I've got what we call the particular solution. So we have a general solution and we have a particular solution. General solution is all of the possible curves with the given differential equation. The particular solution is the one curve that goes through the point that we're looking for. Okay, so as a general rule, when we are going to solve separable differential equations, this is what we're going to do. We're going to have dy dx is equal to some function of x times some function of y. We're going to move all the y's to one side, all the x's to the other, and then we're going to integrate. Okay, so let's take a look at a couple of examples here. We're going to go through a couple fairly simple examples. And when we do this, the main idea is the idea of separating the variables. Okay, so what I'm going to do here is I'm going to rewrite this differential equation. Dy dx is 6x squared over 2y plus cosine y. I'm going to move all the y's to one side, would give me 2y plus the cosine of y times dy. And then on the right side, I've got 6x squared times dx. Okay, at this point, I have everything separated, so I can just integrate both sides. And now it's a matter of using antiderivatives. Now, it's not always going to be simple where we can just take an antiderivative like this question. All of your integration techniques could come into play. You could see substitution, integration by parts, partial fractions, trig substitution. Everything can show up within these questions. So keep that in mind when you get to this point. It's not always going to be as easy as these examples that I'm showing you. So from here, you can see that we would have y squared plus sine y. I'm not going to write a plus c here because I'm going to write a single plus c on the right side of the equation that's going to account for the arbitrary constant on both sides. So the antiderivative of 6x squared would be 2x cubed. And then I'm going to write plus c. Now, typically we would want to solve for y. If we can isolate y and get y in terms of x, we would do that. In this case, we can't do that. Okay, notice they didn't give us a point that our solution has to go through. So the only thing we can find in a situation like this is the general solution. We don't have a particular solution. Okay, so you might be tempted when you're solving these out to just skip straight to the solution. Try not to do that, because I want you to get in the habit of actually showing the step where you separate the variables, showing the step where you take the antiderivatives, and there's a reason for that. It's not just that I want you to show it that way. Number one, it's mathematically correct to show the steps, but number two, you are very likely to have a differential equation on your AP exam that you're going to have to solve by separation of variables, and I want you to get in the habit of doing the steps in the correct mathematical format so that when we get to the AP exam, you're not feeling like you're doing something you haven't been doing all along. Okay, so here's another example. We have y prime is equal to x squared y. So this is a little bit of a disguised differential equation, right? Because when I see y prime, it doesn't immediately look like a differential equation, but remember y prime is dy dx, and that would be equal to x squared y. So now I can separate my variables. dy over y is equal to x squared dx. And now I can integrate both sides just like we did before. And when I solve this out, on the left-hand side, I'm going to get the natural log of the absolute value of y, and I'm using absolute value because I don't have any domain restrictions that have been given here, so I don't really know how this is all going to work out from a y perspective. But then on the right-hand side, just using the power rule, I've got x cubed over 3, and then remember I've got a plus c that's accounting for the arbitrary constant on the left side and the arbitrary constant on the right side. Now, this time I can isolate y. And what I want to do here is I want to get rid of this natural log. So if I exponentiate each side or I use a log rule, whichever way you learned it, that's essentially what I'm going to do here. And so if I think of it as exponentiating, I would have like e to the power of that and e to the power of all of this, right? So that's essentially what I'm doing when I solve this out. So that's going to give me absolute value of y is equal to e to the x cubed over 3 plus c. Notice that arbitrary constant is part of the exponent. It's not written out to the side. It's now become part of my exponent. Well, this is the same as e to the x cubed over 3 times e to the c power. And the reason I wrote that is because what I really want to do is simplify this down a little bit if I can. Now, we've got an absolute value here. When I have an absolute value, that means the right side of the equation could be positive or negative. So that means y is equal to plus or minus, and I'm going to switch up the order here, e to the c, e to the x cubed over 3. And the reason I did that is because when I look at this term, that is some arbitrary constant, right? C could be anything. E to the c is a constant, and it can be positive or negative. So what we're going to do is we're going to replace that sort of messy arbitrary constant with a simplified arbitrary constant. And I'm going to say y is equal to, and typically we use a e to the x cubed over 3. And that would be my general solution. And if you want to, you can say a is equal to plus or minus e to the c. You don't really need to state that. That's understood based on the substitution that we did there. Okay, so that's the main idea. Now, when we look at the solution to this differential equation, down below here, I've got that general solution plotted, and this is what we call a slope field. We're going to talk about these a lot in detail next time, but a slope field is a way that we can represent all possible solutions to the differential equation on one graph, because it's impossible for me to graph an infinite number of curves, but a slope field is representing an infinite number of curves. So we'll talk a lot more about that next time, but what you're seeing in this graph, all these little segments, are slopes at those particular points. And if I were to try to draw a graph based on those slopes, this slope field will predict what all of those curves are going to look like. Okay, over here on the right, I have a sampling of those curves. And if you were to overlay the graph on the right onto the slope field graph, you would see that those curves actually trace right through those slope lines. Okay, so don't get too caught up on slope fields just yet, because we're going to spend a whole day on that next time. But I did want you to see it so you can start to see that, okay, when we graph these things, it's a little bit different. And I also wanted you to have a little bit of a preview of where we're going to go with some of this stuff. All right, so the rest of what is in this section, you're going to have a lot of questions where you're going to have to solve differential equations by separation of variables. Some of them you'll get general solutions, some you'll get particular solutions. But the other thing I wanted you to see here were just some simple application problems. And the nice thing here is these application problems are very, very simple. You're not going to have to do a lot of work with these in terms of actually solving the differential equations. Primarily what you're going to do here is you're going to know, based on the description of the type of problem we're dealing with, you're going to know what the solution curve looks like. Okay, so for example, we saw this back in 8.1. I gave you a differential equation that looks similar to this. dy dx is k times y. So this is a general exponential growth or decay model. So depending on the application, we're going to use this. We might change the variables around a little bit, but this is going to be the same general setup for a lot of these problems. Okay, so when we solve this differential equation out, we're not going to do this every time we have one of these problems, because this works out the same way every time. If you're using a general exponential growth or decay, separate your variables, integrate on both sides, and then in the end, we get this general solution. If you look at those steps, They're a lot like the steps on the problem that we just looked at a second ago, where I talked about the whole thing with the plus or minus e to the c. Same idea here. But we get this general solution, y is equal to a e to the kt power. So typically, we also say at time 0, we have some initial value that we call y naught. And if that's the case, then we can write out our solution to that differential equation in a slightly altered form. We would say y is equal to the initial value times e to the kt power. Okay, so that would be our general solution, where y naught is something that's usually given in the problem, and then k, that exponential growth constant, that's something that we're usually going to have to solve for. Okay, so really these turn into algebra problems. You guys have seen this stuff back in Algebra 2. You may or may not remember that very well, but in Algebra 2, you had a unit on exponential and logarithmic equations, and you went through and you solved some simple application problems. And the application problems were on things like this, doubling, time, and half-life. So this was one of the applications that you saw. And when we do half-life, what we're talking about is we're using an exponential growth model, and we're talking about what's the amount of time it takes for half of your material to decay away. So typically we're talking about like radioactive material that's decaying over time. Well, the way we find half-life is we figure out how long does it take for half of our initial amount to remain. So remember we had this solution that we were talking about when we were talking general exponential growth or decay. Okay, so that's the solution curve that I'm talking about. Well, what we're saying here is, let's say that whatever the amount is that we started with, we have half of that remaining. That's how I find my half-life time. So then I can go through and I can say, all right, if I have half of the initial amount remaining, what's the relationship between that growth constant or decay constant, the k value, and time? And you can see down here, just doing some simple algebra, we can find t in terms of k or k in terms of t. You don't have to memorize those. It's very, very easy to find half-life just by setting your amount at your particular point in time to half of your initial, and then you can solve for the half-life or solve for the k value, but that's very easy to do. Okay, so let me show you an example that is just kind of an idea of the types of problems you're going to see. It says radioactive radium has a half-life of approximately 1,599 years. The initial quantity is 15 grams. How much remains after 750 years? This is essentially an algebra problem. And the reason it's essentially an algebra problem is because it's radioactive decay, you know you're starting from this solution curve. So you don't have to go through and set up the differential equation and solve it. You can just start from that solution curve. So I'm just going to show you my worked out solution here. And my worked out solution would essentially work like this. Here's my general solution. Y is y naught e to the kt power. I know my initial amount was 15. I know my half-life was 1,599. So you can see on this first step, what I did here is I went through and I said, oh, from this, plugging in the values that I know, now I can solve for the k value. Once I have the k value, I can rewrite my solution curve as y is equal to 15 e to the whatever the k value is times t. And now I can find the amount of material that I have at any point in time. So I didn't show all the steps there, but I gave you kind of the idea of how this works. And I show you that, this is essentially an algebra problem. Okay, so another type of problem that you're going to see is a population growth. Now, population growth, you notice here I already wrote out the general solution to this. We have dp dt is k times p. That's the exact same setup as what we saw before. We had dy dt is k times y. Well, we know what the solution is going to look like, right? We know it's going to be p is equal to p naught e to the kt power. We're just changing the variables from y to p. Okay, so same idea. Now, here's another example, and I'm just showing you the worked out solution. A colony of bacteria is grown under ideal conditions in a laboratory so that the population increases exponentially with time. At the end of 3 hours, there are 10,000 bacteria. At the end of 5 hours, there are 40,000 bacteria. How many bacteria were present initially? So again, this is just an algebra problem where, yes, we have to understand what the solution curve looks like, and we know the relationship between the differential equation and the solution. But when we get into these, we don't need to go through and solve every single time for that solution curve. So really, since we know what the solution curve looks like, all we're really doing is what you did back in Algebra 2. And you can see here, I used the 2 points that were given. I used the point in time at 3 hours, we had 10,000 bacteria. The point in time at 5 hours, we had 40,000 bacteria. It gave me a system of equations to solve. To solve this system, I just divided the two equations. And then from there, I can get the K value. Once I have the K value, I can write my population model with the K value plugged in. And then I can use one of those points to solve for the initial population. So very, very easy to do. Okay, so last thing in terms of applications in this section that we're going to look at is Newton's law of cooling. So Newton's law of cooling is slightly altered from the differential equation that we saw for the rest of the problems, but it's still the same general idea. So what we're talking about here is how long it takes for an object to cool based on whatever material the object is made of, and then the surrounding temperature. Okay, so you can also use this in situations where you're going to be heating things up, but it's typically referred to as Newton's law of cooling. Okay, so we have the rate of change of the temperature with respect to time is equal to K times our current temperature minus the surrounding temperature. When we work these problems, we assume that the surrounding temperature is constant. Now, the solution curve for this one is slightly different. So I'm going to go through and solve this so you can get a feel for why this looks a little bit different. Now, remember, surrounding temperature is a constant. So I'm going to separate my variables here. And notice when I separate my variables, I actually have to divide that entire expression, t minus t sub s, in order to get them separated. And once I've done that, this is still very similar to what we had before, because I'm going to have a natural log here, and it's going to be the natural log of the temperature minus the surrounding temperature is equal to KT plus C. Okay, still very much like what we had before. Okay, so when we get to this point, remember we're going to exponentiate on both sides. We can drop the absolute value and then get rid of the plus or minus. So we talked about all of that before. So we get T minus T sub S is equal to A e to the KT power. And then from there, we usually use the idea that the temperature at time 0 is equal to what we call T naught or T sub 0. And plugging that point into my solution curve, I get T naught minus T sub S is equal to A e to the K times 0 power, which means that essentially A is equal to T naught minus T sub S. And now I've got the temperature minus the surrounding temperature is equal to initial temperature minus the surrounding temperature times e to the KT power. Okay, so that's my solution, and then I can just solve for t. And you can see down below here, we solve for t. Now, you might notice that they've got a negative in front of the k, and we have a positive in front of the k. It doesn't really matter if you have a negative or a positive there, because when you actually plug into your particular application, that k value is going to turn out to be positive or negative in the form that you have it. So it's going to work itself out. So it doesn't matter if you write it as a positive kt or a negative kt. Okay, so in the end here, we end up with, some application problems, and I'm going to show you the worked out solution for this one again. The main idea is we've already gone through and talked about how these are essentially algebra problems. So we have this problem when an object is removed from a furnace and placed in an environment with a constant temperature of 80. Its core temperature is 1500 degrees Fahrenheit. 1 hour after it's removed, the core temperature is 1120 degrees Fahrenheit. Find the core temperature 5 hours after the object is removed from the furnace. So notice that we have here a surrounding temperature. So this right here would be my T sub S. And then we also have this initial, this would be my T naught of 1500 degrees Fahrenheit. I can plug that into my general solution there. And now I've got a point that will allow me to solve for the K value, because I know 1 hour after it's removed, the core temperature is 1120. That lets me get that proportionality constant. And then from there, I can get temperature at time is 5. So again, it's just an algebra problem at that point. So when you're solving these out and you're looking at these applications, just keep that in mind, that the applications are very simple. It's not intended for you to solve the differential equation every time. It's intended for you to use the known solution to that particular differential equation and just work it like an algebra problem. Okay, so what I also included here, you do have an assignment in Wiley Plus, and that's where I want you to start. But I also included some extra practice with differential equations. And primarily why I put this here is so you could practice with some more separable differential equations. So I've got some more here that maybe are a little more difficult than what's in Wiley Plus. And then you'll see down here at the bottom a little bit of practice with actually writing out some differential equations that don't follow just the models that were given on those applications that we looked at. But for the most part, it's the same kind of stuff. You can see you've got the solutions here, but it's the same kind of stuff that's in Wiley Plus. It's just some extra practice. So this worksheet's not required. It's just something that I want you to have available to you. So if you feel like Wiley Plus wasn't enough, you can go to this and you can feel like you've got some good extra practice problems that are of the difficulty level that I would expect you to know how to do.